Good morning, everybody. My name is Aileen Yingst. I'm very pleased to be here on behalf of the Heimdall team to talk to you a little bit about our landing site. And let's see how well I do this. Aha. So Heimdall is a CLPS payload. It's flying on the mellifluously named CP-21. We are going to the Gruithuisen domes, along with a number of other payloads. And this is an important thing. I want to give a shout out to all of my colleagues on these other teams. We've heard a lot about the CLPS missions and the first 4 launches that had varying levels of success. I think it's important for folks to know that the missions that are coming up, we're already doing science. You have to do science to prepare for these missions. So science is already getting done. We're already talking to each other about how to maximize that science. And so again, a shout out to all of my colleagues on these other teams for really, in my opinion, having a great model for this kind of working together. So this is the original, the 1973 map of the Gruithuisen domes. You can see northwest, up in the northwest, haha, gamma, and then delta to the south. Oh, haha. This is, it turns out, my first opportunity to talk to a group about Heimdall since it has been finished. We are built, we are currently sitting in storage. Heimdall is over there on the top. You can see us in thermal vac. We are 4 color cameras plus a DVR. We have 80 to 60 degree field of view, and you can see the list of resolutions for the 4 cameras. The 3 cameras, the workspace imager, the panoramic imager, and the descent imager all have the same resolution. The regolith imager actually has best focus at 5 centimeters, which means as we get close to the surface, we have a 35 micron per pixel resolution. We do not have a lander yet, so you can see my goofy little stick figure at the bottom here showing approximately where we expect the cameras to be mounted. And that yellow stick is one of our other payloads. That's the sampler arm built by Maxar. And very early on, we were able to partner with Maxar. So 2 of our 4 cameras are mounted on sampler. And this is why we can get that really, really high resolution, because the regolith imager is actually going to be moved close to the surface. Some test images. Now, for those of you who love calibration, there will be a full up calibration. These were just test images to make sure that we coarsely hit our specifications. So you can see the 360-degree panorama looking a little bit like one of those old pretentious 70s album covers type things. On the bottom left, this is one of those geologic cards that you carry in your backpack when you're doing field work. It's got sorting, it's got grain size, and so on. So there's a red arrow there. There's a grain there that's about 600 microns across, and that is resolvable at about 16 pixels. So you can not only see that it's there, you can tell something about its angularity. And then on the right, this is just our opportunity to try and get some, we turned all the lights off in the room and had a single bit of illumination on JSC1 to kind of have an idea of what it might look like on the moon. This is a list of Heimdall science objectives. I have highlighted the one that we're really going to be talking about today, and that is characterizing and mapping the landing site at multiple overlapping scales. We will have a descent imager, and so we'll have from orbital all the way down to in situ scale to be able to kind of put all of that together for a picture of the site. For those of you who are less familiar with Gruithuisen, here they are. These are the Gruithuisen domes over on the right. On the left is a map that was put out in 2016 by Ivanov et al. The ages that I have listed on the image are from that work. You can see you've got relatively younger Mari and the domes that have been dated at 3.8 billion years, and then the Iridium, and I've spelled that wrong again, Brent, I'm very sorry. Iridium impact off the screen. So why are the Grützeisen domes exciting? They are higher in silicon and thorium. They are lower in iron and titanium than most volcanic products on the moon. And so this suggests a different eruptive mechanism or different eruptive history, different environment in which these domes were formed. They also have a different morphology. You can see that there are these, right, as opposed to the flat Mare material. So there are a couple of hypotheses. The late stage hypothesis, where you have fractional crystallization, and that should have two L's, I apologize. Fractional crystallization at the end of eruptive life, or the early stage hypothesis, where you have remelting of a high silica crust at the beginning of eruptive life. The problem right now is that if it's late stage, that requires that we explain the older age of the domes. If it's the second one, that requires presence of a pre-existing higher silica crust or a higher silica source to melt. And of course, there's the alternate hypothesis, which is they're not related at all. So the first step in trying to deconvolve what's going on is mapping. We have some mapping scales here listed. So you have in the white box, the large white box, that's going to be our regional scale map. You have a couple of smaller boxes. These are at 1 to 50,000 scale, and then the actual landing site, and I'll show that because it's very, very small. I'll show approximately where that's going to be in a future slide. That's going to be 1 to 5,000. And then, of course, there's crater mapping that's involved. And we think right now, if we do a conservative 10 pixels across kind of mapping, it will probably get down to about 1 to 300 meter diameter craters. This is a list of data sets that, Brent Gary is our chief mapper. He's put these data sets together into a project that we can use to map. One of the important things about this mapping effort is we want to make sure that each type of data set gets its due. So you've got geomorphology, you've got topography, but you also have some compositional data. And it's important that that compositional information is not lost as you're doing the mapping. As you know, you don't want it to kind of come in at the end and sort of lose some of the unique information that you can get from the compositional data. So one of the things I'm showing here, this is a traditional sort of Clementine 3-color ratio image. For those of you who are less familiar with that, the blue and red that measures the steepness of the continuum slope. So a shorthand of that is that if your material is bluer, it might be fresher. If it's redder, it's more mature. And then the greener tones would indicate the presence of an FeO absorption band at approximately 1 micron, with a little shift here and there depending on what flavor of pyroxene you have, for example. And so you can see even in this image, and I just want to point out a couple of things. You have some craters here that are greener. You have a couple on the dome that are bluer. That suggests that you've dug up fresher material. And then right at the bottom here, I want to make sure I don't like zap the screen or something, but right at the bottom here, you can see this blue tag at the end of this peninsula. And then right below that, this green area. Well, I'm going to talk about that in just a second. So this is some approximate line work that we've started. And by we, I mean Brent. Thank you, Brent. Just some important places to point out. So I'm going to talk about those white arrows in just a second. That black arrow points out this peninsula, and you can see from this image pretty clearly from the derived topography that the texture of that area matches more or less the texture of the area sort of to the west. And that is an indication that you're looking at iridium ejecta, right? So in the 1973 map, actually that peninsula was mapped as part of the entire dome. Later on, when I showed you the Ivanov et al. Map, that was separated out. And we think that's absolutely correct based on the topography and the surface texture here. The blue arrow, again, I'll talk about that a little bit more in a moment, but the blue arrow here, you've got this very rough sort of almost polygonal texture over here. And then just as you go up the dome, there's a slightly different texture from the slope of the dome compared to the texture around it, which is a little rougher. And what we think is going on here is you might have a mass wasting event with the material down below. If I go back, you can just see in that area that rougher texture material is bluer. It's been uncovered, right? You've got some fresher material that's been uncovered. And again, these white arrows, this is actually pretty darn cool. So both of these white arrows show the base of a sinuous rill, right? That kind of comes in near the dome. Now, the one on the top of the image that you're seeing here is a little bit harder to see. I'll show some different perspectives of that area in a moment. But the one here at the bottom, if I go back, you'll see this kind of blue area, and then right below it, this kind of yellow-green where the sinuous rill comes in. And both of those areas are important and need to be part of the map because they suggest that you've got a sinuous rill that comes in, there's a depression there, and it looks like you've got some mass wasting, which has uncovered this younger stuff, right? As the sinuous rill, I'm losing the word, I'm sorry, but as the sinuous rill comes in, you've got mass wasting as it's undercut by the volcanic activity. So that was just a really quick rundown of some of the initial things that we're seeing. And that little red dot is where we're hoping to land. And you can see it's very near this sort of topographic triple point of this smoother, flatter stuff, a little bit of a higher topography right there, and then right near the slope. So just to end up, I'm going to show you a couple of really cool perspective images of these domes. And so again, one of the tags is lost, but it's northwest down to the bottom, gamma, and then delta. Here's another look, and you can see those white arrows. The white arrow over here is the peninsula, and you can see much more clearly that depression that's been left as the sinuous rill comes in. Here is that area again over on the far left. And then I do want to point out that these are the kinds of things that are going to be really important to help us understand the stratigraphy of what happened first and what happened next and so on. So we're right at the beginning of trying to piece together the stratigraphy and the history of this area before we land and really fill in the details. So I'll leave it there. Thank you very much.
Thank you very much, Aileen. We can have a quick question. I don't see any. You were perfectly clear. Great. Thank you so much. Our next speaker is Wes Patterson, and he will talk about LRO Mini RF bistatic observations of Cabeus crater revisited.
Thank you.